Hello everyone. Today we will discuss about the 4-bit shift and add multiplier. This is a second experiment. To start with, we have to write the Verilog code, verify the functionality, and then we have to synthesize by using the constraints and generate the report. So first let us look at the working of the shift and add multiplier. To start with, we have to consider two 4-bit numbers. Here we have considered 9 and 12. Let 9 be a multiplicand and 12 be the multiplier. It is x and y. This x is assigned to m and y is assigned to q. Let us consider 4-bit accumulator, and since it is 4-bit, the n value will be 4. To start, initially we have to check the q0 value. It is a 4-bit, so the least significant bit has to be checked, and if it is 1, then the accumulator is added with the m value and it is stored in the accumulator again. After that, the new value of the accumulator and the q value is concatenated and right shifted, and after this step n value is reduced by 1, decremented by 1. If q0 value is 0, then we don't have to add the accumulator to m. Directly we concatenate accumulator and q and right shift it. After this process, after this also the n value will be decremented. So for every cycle n value is decremented, and finally when n becomes 0, it comes out of the loop. So in this example, as we told, we have considered 9 and 12. Well, 9 will be the multiplicand and the 12 is multiplier, which is y. So this is the decimal equivalent and this will be the binary equivalent of it. We have considered the accumulator, which is a 4-bit number, and the y is q and x is m, n value is 4. So now initially the accumulator 0 0 and the q value, this 1 1 0 0 is taken, and now the q0 value is verified or checked. Here it is 0. Here we see q0 value is 0. Since it is 0, the accumulator and q is concatenated and it is right shifted. Once we right shift, the new value we get is 0 6. It was 0 9 and it was 0 12. It was 12. So then we have what we have got is now it is 6. This it is next is again this accumulator value is written here and the new value of q is written here, and again the q0 bit is checked, and again this q0 is 0. So accumulator and the q value is concatenated and it is again right shifted. So we get 3. So initial value was 12, 6 and now 3. Now again the accumulator value and q value is written down separately. The higher 4 bits will represent the accumulator value, the lower 4 bits will be the q value. Now again q0 value is checked and we see now it is 1. Since it is 1, the a and m, this is a and m has to be added and then right shifted. The a accumulator and the m value here, this is m actually, not b, this is m, it should be added and right shifted. So we'll add the value with m, m value is this, so accumulator is added with m, so we get the new value of accumulator. This new value of accumulator and this q, now this q here is concatenated and right shifted. Next again the higher 4 bits is written as accumulator and the lower 4 bits is written as q, and again q0 value is checked, and here we see this lower bit is again 1, so we have to add the accumulator to m. This is m, not b. So when we add the accumulator value to m, here this value of accumulator is added with m value. This is this value of m and this is a new value of accumulator. This new value of accumulator along with this q is concatenated and again it is right shifted, and finally we get the final result as 1 0, that is 108. And here we see every time n value, initially it is 4, after the first step it is decremented, it becomes 3. Next again it decrements, after this step it becomes 2. Next here again after this it gets decremented and it is 1. After this step it is decremented and it is 0. Since it is 0, it comes out of the loop, and finally we get the result. Now coming to the program, let us look at the program here. This is the program that we have here. If we look at the program, initially we declare the inputs and the clock, load, then reset, and the AB value. This is nothing but the X and Y in our case, and the product, which is an 8-bit. Since it is 4-bit, the product will be 8-bit. Then we have taken register, that is accumulator, Q, M, all these are considered, and the initial value of count, that is n, is 4. Now with respect to the clock, that is always at the pause edge of clock. If reset is 1, then all the initial values are 0 and the count value is set to 4. The product is also 0. Then if load value is 1, with that is when load value is 1, the accumulator value is put to M, and that is X and Y value. Here A value is put to M and the B value is put to Q. And then we start now verifying once it is here. Now after this we start verifying the Q0 value, and if the Q0 value, that is if the Q0 value is 1 here, with the count value being greater than 0, then we see that the accumulator and M value is added, and then after it is added, the accumulator and the Q value is concatenated and it is right shifted by 1 bit. Now again the higher, after it is done, the higher 4 bits of P is taken as accumulator and the lower 4 bits is taken as Q, and after this one set, the count value is decremented. Suppose Q0 value is 1. In this case, when we have verified it for Q0 being 1, suppose Q0 value is 0 and the count is greater than 0, then the accumulator addition is not done. Directly the P value is taken, the it is concatenated and right shifted by 1. Then again the higher values, higher 4 bits is assigned to accumulator and the lower 4 bits is assigned to Q, and after this step also the count value is decremented by 1. So like this, every time the Q0 value is verified and accordingly action happens, and after every action the count value is decremented. Finally, when the count becomes 0, the final product is taken as the concatenated value of accumulator and Q. So this is the program, and this is the test bench that we have written. Initially we have taken this model, then module is taken, and then for that all the registers and wires are declared, then the unit under test is also declared. Then always we take a clock which keeps negating for every 10 nanoseconds. Then initial that is when clock is 0 and load is 0. Then we have the that is here, if you see, this is output. I've just shown here. Initially the clock keeps negating for every 10 seconds, and initially when the that is here, that is when clock is 0 and when load is 0 here, when we have the load value, this is the load, when load is 0 and when reset is high, the value of A and B is taken. Then at 20, that is 20 nano, the load becomes 1. That is what happens when the load is 1 is we have seen when the load is 1, the A value is pushed to M and B value is pushed to Q. Then here after this, at 40 nanoseconds, the load becomes, this is the load, the load becomes 0, and reset is still one, I mean here reset is made 0, the reset is made 0. Then after this, the multiplication happens, and we can see the result. Okay, we will see the result for the program that we have done. For this input that we have taken, we will see the result. We'll go to the multiplier here, and open the terminal. Here we have to we'll be using the NCSum simulator here, and the NCSum simulator, it is going to check the functionality of this 4-bit multiplier. First we will invoke the CSH command. Okay, this is the shell command which is used to execute the C scripts or the commands in the cadence. Then we will use the source slash home installed slash CSHRC command. This command ensures that the environment variables and the path from the CSHRC files are available. All the configurations and commands are available for us to do the simulation. Then once we execute that command, we get welcome to cadence tool. Then here we call the NCSim simulator. From this NCSim simulator, once we have this, we have to we have to select all these, and now whenever we have to do the verify the functional simulations, we have 3 steps involved. Basically, we have to compile our design. First we have to compile the design. Here this symbol is used to compile. Next, once we have compiled, we have to next elaborate the design. Elaborate is to build the hierarchical model for our design. So here we will elaborate our design. Once the elaboration is done, then we have to simulate. We have to check for the waveform. So this is the output that we have got. When we verify it with the, you can just verify it with the this is the test bench we have written. So now the clock keeps negating, then initially when the clock is 0 and the load is also 0, with reset 1, A and B values are considered. Then at 20 nanoseconds the load becomes 1, wherein the M and Q values are taken. Then after that, at 40 seconds we see the load again, I mean at this point, at this after 40, from 20 after 40, that is at 60, the load becomes 0, and at the with the reset being 0, when reset and load is 0, the counting, I mean the multiplication happens. As we have seen, that is in this, then we have to get 6, 3, 73 and 108, 6, 3, 73 and 108. So for in the 4 steps, these are the results that we get. Now this is verifying the functionality. So now the first half is done. In the next half we have to check for the we have to synthesize our design. We will now simulate our design and see. To simulate the design, whenever we simulate, actually the simulation is done using genus tool. In Cadence, the simulation is done using genus tool. How this genus tool will work is, it will take the RTL code, the Verilog code that we have written, and it will take the constraint of codes if we have written any, and it will use the library files, and it will generate a gate level netlist, and also it will generate a report, that is area, timing, all those reports it will generate. So to start, we have to write the constraint file. So this is the constraint file that we have. So what this constraint file, what it is, what do we have in this constraint file is, if we look at this, the first thing here, create clock, is nothing but it defines a clock. The first syntax here will define a clock here, and the clock, it has a period of 10 nanoseconds, and the waveform, that is here the waveform rises at the 0 nanoseconds and it falls at 0.5 nanoseconds, that is it will have a 50% duty cycle. Next here, rise time and fall time. What here, set clock transition, rise is 0.1, fall is also 0.1, means it sets the rise time and fall time of the clock to 0.1 nanoseconds. Next here, the clock, it defines an uncertainty margin of 0.01. And next, in these two syntaxes, it is going to set the maximum delay at the input and the output to be 1 nanoseconds related to the clock. Next, coming to the what we have is the RC script. So what is done in this RC script, what do we have in this RC script is here, this actually this is a TCL file. TCL file is nothing but the tool command language file, which will which the genus will execute, and it will synthesize and generate the report. So what are these commands? What are these commands here is, set db means it sets the library. Here this is used to set the database. In the database is set based on the technology, that is we are right now going to work with 90 nanometer technology. So it is going to set the database for this 90 nanometer technology, that is all the design rules and all with respect to that will be considered. Next, it is going to set the path where we are going to write. This is the folder in which we have the shift and add Verilog code. So it will set the folder or the path where we can, where it will find the Verilog code. Then after that, it is going to next it is going to set the database setting is set to slow means here it is going to consider the worst operation the worst case operation conditions, and it is going to synthesize the design. Next, it is going to read our Verilog code, and then it is going to elaborate it with the constraint file. Here it calls a constraint file and it elaborates. Then here the next three commands are used to translate and map and optimize. Here set generic means it sets the synthesize effort. Here the synthesize effort is set the date, that is the database or the it is going to set the database setting. The generic effort, that is the synthesis effort, is set to medium. Then next it is mapping, the mapping effort is also set to medium. That means it controls how much effort the tool has to put in mapping the design to the that is the present technology or the target technology library. Next, optimization, the optimization level, to what extent it has to optimize also, it is set to medium. Then all this is to generate the report. So this is about the RC script, and here for the synthesis we have to write the constraint file and the RC script file. Once we have done that, then we can go to the root, and then we call the genus. Genus is going to execute our RC script. This is the output, and this is the gate levels, or the synthesized result that we have got. That is all the cells, every that has been synthesized for our designs is here. Then when we go to the folder, we can see the power report. The power report is there. Then we can check the netlist. This is the netlist that we have. Then this is the timing report. We have the timing report. So all the reports will that are generated, the area report, all the report generated will be in this folder. So this is about the simulation and synthesis of the design. Thank you.